be hearing about hidden biases in data and whatever that means. So I'm going to talk a bit about how some things came to be. I'm going to talk about this simulation I've built and how it works and what we use it for. So it's going to be part data science and part actually game design. So I guess it's going to be still interesting to most of you. And I'm from this company, which is not far from here. It's here on Novi Belgrade or New Belgrade, so you can, if you don't know much about the company, you can search it on the internet. There's like very cool stories starting from how it was founded to things that we do, like the thing I'm going to present today. So I started working in 2012, and back then, looking from this perspective, like everything was kind of maybe not in infancy, but like its teens. The whole field was very weird. You had only Hadoop, and you needed like very specialized person to operate it. Now we have like much happier tools to work with data. So in the beginning, I worked on data infrastructure because we needed to know what's happening, some internal BI tools, but I quickly moved to Top 11 and worked on its enormous data. The game has like millions of users. We collect around a billion rows of data each day. So I did all your usual data science stuff there, like A/B tests, forecasting, some machine learning, things like that, exploratory analysis. And again, looking from this perspective, this is kind of how we treat our data from the game, like this huge mystical black box. So even though we build the games, and in case of Top 11, it's maybe even more pronounced because we started doing the whole analytics thing maybe 2 years after the game has launched. But even even for other games, this certainly contributed to the fact. But in general, even though we build games, we kind of treat data as coming from the black box. And if you see the tools, it kind of becomes evident. So I quickly moved to Spell Souls after that, and it was sort of an experiment because the game was in production still. It had zero data, and the idea was to see like what data scientists can do in that phase of game development. And on this project, one day, lead game designer came to me and asked me, do I know Excel and how well do I know it? And I was a bit confused. It turns out that he actually wanted me to build a simulation of game economy. But up to this point, if I learned anything about data coming from the games, it's that this normal distribution, which we usually think of when we think about random things and distribution, is actually more of an edge case. I've almost never seen it in the real data. And I know very well that averages lie. So if you replace all the fish here with the average fish, I think they all get eaten. I'm not really sure, but so one of my first design decisions for the simulation was to actually simulate the populations and not some average users, which we usually do. And I quickly came to this, let's say, architecture for the simulation. It's top-down and bottom-up. So I start from cohort KPIs, from engagement KPIs such as retention, average number of sessions and playtime, and then I generate users in the simulation such that they satisfy these high-level distributions. But there's also part where you need to have more or less consistent behavior of each of the users, because otherwise it's not very useful. So once you have this user level, let's say, engagement and behavior, then you need to define your game system and how they're going to interact with it. The simulation actually tracks everything like production game would be tracked. It literally has like events, and then you can analyze that and see the connections between this, let's say, input data that defines the scenario of simulation and the actual outputs, which are game-specific KPIs, and I'm going to touch some of those later. So how it works, if I have this population of users in a cohort, I randomly generate engagement score for each of them at the moment of generation, and it's something like this, just a random number, which we're going to represent like this. So green is higher. And then let's say I want to define how many sessions each of the users is going to have. So intuitively, engaged users should have like more sessions. Those who are less engaged should have like 1 or 2. And that's precisely what actually happens in the simulation. So it's almost it's distributed in this almost ranking manner. So this satisfies that users who are engaged are always the ones who have like more sessions, and they're more likely to play. So you can see that here as well. So on retention curve, and this is just sampled for some key points, key dates like 1, 2, 3, 7, etc., just to avoid visual clutter. So intuitively, people who are more engaged, they should be playing longer, they should be playing more often. And those who are less engaged with your game, they actually churn out quickly. And that's what you can see, like from the day 0 to day 1, you lose most of those yellow and red users. And this kind of creates a general framework where you actually have users with more or less consistent behavior and consistent over long periods of time. And this is very important for mobile games, because I could argue that the actual game that users are playing for long periods of time is actually the core loop. It's just this simple set of actions they're repeating each day. And because this is almost always heavily influenced by their activity, we actually need this first layer to correctly predict their journey over long periods of time. So once we have this engagement, once we know their airtime, their playtime in the game, they now need to interact with game economy and game systems, and these two guys thought a lot about how people make decisions in such systems. So you might recognize the right one. The other one didn't get his blockbuster movie yet. So both of them got Nobel Prize in economics. Daniel Kahneman is well known for the book Thinking Fast and Slow, and he's the guy who introduced us to biases in decision making, and John Nash gave us this mathematical tools to reason about behavior of so-called rational agents. And I'd say that often when we think about players who play our games, we tend to think about these biases and how games are more art, and how they often make some irrational decisions in the games. And I think we underestimate that they're actually very rationally interacting with the systems that we design, and that's what really helped me in developing this simulation. So altogether, you start from this high-level metrics, which define how much they're going to play. Then we get individual behavior. We define game system. We define here the behavior, how they're going to interact with it. And then this is maybe the part that's like sort of a dark art, because you need to define it in some simple way, but basically you need to take into consideration both rational, optimal way how they're going to interact, and maybe this notion of how they're going to diverge from this optimal behavior. And in the end, you get lots of data which could be immediately analyzed in Tableau, and I use Tableau. And what you end up is you get for certain scenarios which you define with certain assumptions about their overall activity, their behavior, etc., how some of the metrics are going to look like. And this is very important for, I think, both the game design and also data analysis. So let me give you the first example of how we use this. So the general narrative about chess with timers is that they're a great retention tool because they schedule the next session, etc., etc. So we wanted to know how well does this actually work. We tried to optimize it with not much success. So once I got this tool to a point where I can use it for also data analysis, I could actually define the baseline, which in this case would be how much people would play if they're not affected by this fact that this like behavioral pattern of coming back to the scheduled time to play the game. And this is not possible to get from the real data. You'd have to basically build different game, and then it wouldn't be good for comparison again. So in the simulation, I know that they are not affected in any way because I defined that in the code. I have players basically playing on random, which you can also treat as they play when they want, as much as they want. And the end result is a metric that shows how many chests are opened each day. And if you balance the numbers correctly, what you get is basically this baseline, which is very elusive. And it turns out that it's the same number of chests that are open. It's the same curve as in production game. And this was like very surprising result because people mostly play the game the way they want. It's actually not affecting their behavior much. So the second example is pair retention, which is very interesting metric for all of us, but it's a bit ill-defined from the perspective of data warehouse theory. So we tend to value our pairs a lot, and this is a metric we often look at. And again, the usual narrative is that people have great retention because they're paying. Once they pay, they become very loyal users. I'm sure we all heard those ideas. But I actually wanted to know how much are they affected by paying, and how much the act of paying is affected by their first experience with the game. And this is again the problem of causality and correlation, which is really hard to solve in general. But I actually used very, very old tool from science, and I thought, like, okay, let's imagine that we have this silent labeling system in our game, and people actually can't pay. They're just marked somewhere as pairs. So we're gonna pick random number of users, which is basically the same as the number of users who would usually pay. And the first time you select them in this process, you just mark them as like pairs. And that's it. They don't know they're marked anywhere. They don't get anything from it. It's just some label somewhere in the system. And then the question is, how does retention of people who are labeled in this way look like? And you might be thinking that it's basically the same as everyone else's, but the thing is that you label them only if they're active. So you're only selecting active users, because people can't pay if they didn't log into your game, right? What you end up is this. So the orange line is actually retention of these false pairs. And the reason is, if you go back to the graph I showed, how does engagement actually look like over time in retention. Well, over time, you're losing less engaged people. And those who are more and more engaged, they actually remain in the game. So when they pay, they're actually self-selecting from the group of highly engaged people. And over time, so if they convert later on, there's higher chance that they're going to be actually more engaged. And this good numbers are actually paid by the fact that you lost a lot of people who would potentially be pairs, but have actually churned before they have correctly labeled themselves. So this is actually the difference between retention of real pairs and these who are labeled in this way. And this whole data is actually generated by the model I've built into simulation. So I could play with it in ways that I couldn't play with these black box models who just look at the end result of data. So now I have a process that kind of defines how the data is produced. So this also created much deeper cooperation between data scientists and game designers, because we would sit down and discuss about how they expect for people to behave, and put the whole thing into simulation, and end up with these baseline metrics that we can use later on. Once we get real data from the game, we can quickly figure out what is working and what is not working. Have our assumptions been wrong, or has something in the system been wrongly designed? It also allows for much faster iteration, because for some things, not all of them, you can actually test your system on the simulation. You can see how their user journey is going to look like, and quickly iterate on that. Of course, you can't get the real behavior from players, but this is the part where if you have good baselines, you can quickly iterate again much faster in production. And that's it. Any questions?
Yeah, hi, thanks for the great talk. I would like to ask you about the cohort KPIs that you based your simulation on. Were those benchmarked on other games, or provided from the game designers as some desired state the game should look like?
The idea is to start with some numbers. So we did this even before launching the game. We used cohort KPIs which we presumed are going to happen. As soon as we got some data from the real game, it can go back to the simulation, so you can also iterate on that part.
Yeah. Okay. Thank you.
Hi, can you maybe tell us of some example where you use this simulation in order to get some very different conclusion than from the game, meaning that you come up with something that is totally different what game designers thought it should be. Because you mentioned chests and the opening of chests,
Right.
and you said that from simulation it can be seen that it's almost the same as in, like, from your simulation, almost the same as in the game. But can you mention something that it's like completely different, maybe something counterintuitive or something like that?
So, well, this was pretty counterintuitive because, well, not counterintuitive, but counter the current narrative. So it's great mechanic. Don't get me wrong, but it's not used for retention actually. It has other purposes. What's interesting here is that when you build the simulation around this average user, people often do assumptions on population level, and then they simulate single user. So, and this is hard because we have really bad intuition about reasoning, about the processes that create this skewed data you see in games. And here you actually have this whole layer that's like simulating populations, but what you end up is you're thinking about individual user, like what's he gonna do? And good example was when we were building economy for Spell Souls, we had in Excel again this let's say checkpoints, how much what's the average level of certain types of cards after, let's say, n days of play. And what I did is, instead of setting these high-level goals, I defined, let's say, low-level behavior. How are players going to use the resources they have? So what's the most logical way for them to do it? And it ends up showing that some of these numbers actually can't be achieved. I mean, they could, but they're not really natural thing to happen in such a system with, economy that looks like this and prices for upgrading certain cards that look like this. So it was completely, different perspective that gave us immediately different insights, and then we built from that.
So in your what do you put like more focus on, like those simulations or A/B tests? Yeah, because like there are actually two different approaches to check specific hypotheses. Of course, I understand, like, the probably the simulation is a bit more repetitive, but then it's based on some assumptions versus the test is just the test. Yeah.
Yes, so A/B test is still a great tool because you can infer some behavior that's inherently human. But again, if you have good assumptions, then you get some numbers from the simulation which you can compare. Then, if they're close enough, then your assumptions are good. And the great thing is that you can actually learn much quicker about these assumptions. And then again, A/B tests really help with this a lot.
So thank you very much. Please, another round of applause for Marko.